In this video, I'll be looking at the dynamics of motion of connected particles or connected masses, still under the applications of Newton's second law of motion. For some time now, I've been talking about applications of Newton's second law of motion. Here we have two masses that are connected together by a string, and the string is made to pass over the groove of a very smooth pulley. Now, one of the masses, M1, is resting on a surface, horizontal surface, and the second mass is left hanging in space. And you can see the two masses connected together. Now, we're going to do the analysis and then solve this problem. Given that mass M1 is 5 kg, M2 is 3 kg, we have to calculate their common acceleration, because one thing here is that the two masses, if allowed to move in the first place, they accelerate at the same rate. That is, M1 accelerates in the horizontal direction and M2 accelerates in the vertical direction. And then given the height of M2 above the ground level, let's say 5 meters for instance, what will be the speed of M2 just before it hits the ground? We are still going to look at that. So let's look at the first case here. Case 1 is when there's no frictional force acting between the two surfaces, that is the surface of M1 and the surface of the horizontal table or thereabout. Okay, so I'll take that, as case 1, a smooth surface. When the surface is smooth, meaning that no frictional force, acting. In this case, the coefficient of static frictional force or static frictional force is 0. Now, let's see for the horizontal motion. Let's resolve for the horizontal direction. Resolving along the x-axis horizontally, that is along the x-axis. Now, the only force acting on mass M1 is force T. T is the tension in the string. I can decide to maybe include the forces acting on M1. Okay, I kind of drawing the free body diagram. Okay, another force acting on it is the weight of M1, which is M1 times G, and there's a normal force acting from the stable surface. We'll call that N. Now, these two forces, of course, when I'm resolving for the direction of motion horizontally, they don't contribute to the acceleration of M1 because they are not acting in a direction of motion. Resolving horizontally, we have that T is equal to M1A, equation 1, that is applying Newton's second law of motion. T equals M1A. Why is this so? Because that's the only force acting in the direction of motion when there's no frictional force acting. Then resolving vertically, so see now resolving vertically, we have, here too, let me include the other forces acting on M2. One is the weight of M2, and the second is the tension, which opposes the motion of M2. If the downward direction is taken as positive, okay, I'll take this direction as positive, which means any force acting upward will be taken as negative. Therefore, I have my M2G minus the tension T equals M1A, equation 2. Okay, so this is the case when there's no frictional force acting. So adding these two equations, I have T minus T, that is 0. So what is left is M2G is equal to M1A plus, this is M2A, equals to M2A. So that if I factor out my A, that gives me M1 plus M2 is equal to M2G. All right. So that A equals M2G over the sum of the masses M1 plus M2. Okay, given that M1 is 5 kg and M2 is 3 kg, what do we have there? We have 3 times 10, taking G as 10, over 3 plus 5. That gives me 30 over 8. Okay, that gives me 4, that's 15 over 4, which gives me 1.75 meters per second square. So this gives the acceleration of the masses, and that's their common acceleration. They both move with a constant acceleration of 1.75 meters per second squared. Whether it's for M1, which moves horizontally along the table surface, or with M2, which moves vertically downwards. They both accelerate at the same rate. Okay, the next question says you find the speed of the block M2 just before it strikes or hits the ground. Okay, we can take one of the questions of motion. Already, if the block starts falling from rest, the initial velocity of M2 is 0. You have to find the speed unknown. The distance is 10 meters. The distance is 5 meters above the ground, and the acceleration is 1.75. So using the equations of motion, v squared equals u squared plus 2as. I have this is v squared equals 0 plus 2 times acceleration 1.75 times the distance 5. So which gives me v squared equals, this is 3.5 times 5, which gives me 17.5, and taking square root of that, that gives me square root of 17.5, 4.2, roughly 4.2 meters per second. Okay, that gives the speed of block M2 just before it strikes the ground. So that is the first case when there is no frictional force existing between the surface of block M1 and the table surface. Okay, let's analyze the second case. Frictional force exists. This time I want to analyze for the static frictional force. Frictional force exists between the surfaces. Okay, so we want to write down or derive an equation, a formula for the static frictional force that exists, static friction that exists between the two surfaces. I call that Fs. I recall that static frictional force is also the maximum frictional force, the limiting frictional force, the maximum force that must be overcome just before a body is set into motion. So before a body can just move for the first time, that force must overcome. In fact, static frictional force is also the keeping force, the force that keeps a body at rest on a surface without sliding along the surface. So before a body can start sliding, can start moving along that particular surface, that force must be overcome. All right. So, but this time around, we are going to look at it in this perspective. Just before block M2 jerks forward, just before block M1 moves forward, that force that must overcome is a static frictional force. In that case, for resolving along the horizontal surface, okay, maybe before then, let me include my Fs, which is a static frictional force that opposes the motion, because when M1 is just about to move in this direction, okay, so let's call the direction of motion, because of this pull, the tension here, from this particular mass M2. So before it moves in this direction, this one will quickly come in, that is Fs, to oppose the motion of block M1. So in that case, resolving along the x-axis or along the surface, I have T minus Fs is equal to M1A. That is from Newton's second law of motion. That's the resultant force acting on block M1. Okay. Now, since this body is yet to move, we say just before it jerks forward, the acceleration of the two blocks is 0, meaning that T minus Fs, that is static frictional force, is equal to 0. Okay, so resolving vertically, okay, I have want to take M2G as my positive direction, that is direction of M2G. So I have that minus tension T equals M2A. And since again A is equal to 0, this reduces to M2G minus T is equal to 0. Okay, let me call this equation 1 and then label this equation 2. Now, since the tension in this string will be equal to the static frictional force Fs in this case, I'm going to substitute that in this equation 2. That gives me M2G minus Fx is equal to 0. Okay, which means the static frictional force is equal to M2G. Now, suppose I'm asked to find the coefficient of static frictional force, acting between the surface of block M1 and the horizontal or table surface. Of course, you know that coefficient of static friction is defined by this equation. Frictional force Fs equals mu s multiplied by normal reaction. Okay, because you know from one of the laws of frictional force, solid friction, that frictional force is proportional, whether it is dynamic or static, to normal reaction. And here, normal reaction is equal to the weight of the block M1. Okay, so this is where we need to apply the forces acting vertically. The normal force is equal to the weight of block M2, you know, since the block is at rest in that direction. All right, there's some motion along the vertical direction. Okay, so making my substitution, I have Fx equals mu s multiplied by m1g. So if I call this, let's label this equation 3. I want to make substitution into equation 3. Okay, so I have my mu s m1g is equal to m2g. That is bringing back equation 3 here. G cancels G, so that my coefficient of static friction is this ratio of the two masses, M2 over M1. Okay, once again, let's evaluate that. M2 was given as 3 kg. Come back to the question here. M2 was 3 and M1 5 kg. That gives me 3 over 5. That gives me 0.6 without any risk. Take note that static frictional force, coefficient of frictional force, has no unit. So it's more like a dimensionless constant or a dimensionless variable, because it varies from one surface to another. And it's just simply the ratio of the two masses. And you know that for static frictional force, I know that for coefficient of frictional force, the range of values of coefficient of friction is between 0 and 1, which means that if a body must have, or if a surface must have its coefficient of friction of 1, means it must be a perfectly rough surface, and it must have if it has a coefficient of 0, it means a perfectly smooth surface. So the value ranges from 0 to 1. So if that must be so, it means that block M2, the mass of M2 must be less than M1. All right, so that is the case for when there is frictional force, when there is no frictional force. So in the next video, I'm going to analyze for the dynamic or kinetic frictional force. So follow me in my next video. Please like, subscribe, and share. Thank you very much.